I send them your. Oh, we're going to do it anyway. So yeah, that's right. I used these glasses photos for some profile the other day, and I got like 500 comments, and I had like a photo that couldn't handle the like funny. Thanks, James. Please. I thought it was Cassandra. What about?
No.
Sorry, I'm good.
Holly, nice to meet you.
Holly, your name sounds familiar. You been on some.
Ready? Try my best to hopefully envision, like, try to use your eyes and get that swiping.
Good. So, between the,
Hopefully you appreciate it. Yeah.
it's like an unearthed before.
Every hackathon there, like, we should not hackathon to see if someone can just do all these things at once every time.
God knows why. Might be. Oh, that isn't the case.
All of this stuff. Machines and things, man. Expect you to work all day, they never nice to it, always dusty. It's like, no, not good. This is what happens when you
It's working? Yeah. It must be something to do with the cable. You pull it out, you put it back in,
Thank you so much.
That's right on that link.
This is a personal iPad. Oh, tricky. It's like really yeah, that's my picture.
Oh, I just want to make sure this thing works. I need to start sending They all have to be no, that's
I think it's your name on it, so I think you're gonna.
Yeah.
Yeah, anything you can talk me at all? I mean, I'm not a great beer picker, but
Whatever's called.
maybe Jake can pick one for you.
No, I'm alcohol free. Drive your life. You're going to drive your life. No, my wife. Yeah, that's right. I'm Perth based. I was the guy that was responsible for sending me through that crazy Manchester experience. That sent us, then ended up in France. Around the dates for just because and the original 94 letter that's still appendix at the back, which I think is I must have mentioned. Yeah. It was Matt, right? It was, yes. So you guys ready to go? So yeah, my laptop.
Pick Brody or Summer Ale?
Brony sounds great.
There you go.
Sorry.
Easy.
They might be 5 minutes. Just so you guys know, we'll put all the team names in here, but we have switched. All right, good. Everyone together. Hello, everyone. Hello, everyone. If you can, come on down. We're going to get started here shortly. So please grab your last drink, some water, beer, wine. Come on down, please. Take a seat.
Yeah, I will. So it's gonna get the back of my head. Right? How are you, by the way? Yeah.
I don't know why. He thinks it sounds good. It sounds like something. Sounds like
it's Don't be shy. You don't have to sit in the back. I promise we won't bite. Come on forward. Please take a seat. Come on forward. Please take a seat.
You're so good. We need to hear you twice today. This was gonna get a long way.
Okay, everybody. We're gonna have some double audio for 1 second.
You're in the middle of it.
All right, everyone, we'll get going here, promise. Really, if you're in the back, please come forward. We don't want you to get lost. So we'll do a quick opening presentation, and then we'll get what you guys are waiting for. We'll get down to the final presentations from the deliverables. So that's me. I'm a director of Unearth. This is our first full hardware hackathon. So it's not the usual that we've done over a quick weekend. It's been extended to be done over the 2 weeks. And I think the hardware is a bit more complicated, and it's been shown, but the results are better, which is great. So on Earth, we believe in the power of entrepreneurship to change this industry. We're super excited about what innovators, developers, and entrepreneurs can do in the resource space. We've run a whole bunch of events across the globe. This is our first hardware hackathon with great global participation. We're excited about running this one and many more. And if you don't know, there is a massive amount of disruption coming in the industry. What you guys did is part of it, and it's going to continue to go. That number is just by 2020. It's massive. So Digital Tribes, this event, it was global. Even though you're here, we are live streaming the results. So we have people tuning in from around the world. We had participation from 1, 2, 3, 4, 5 different continents. Digital Tribes and this initiative within BHP is really about jobs in the futures, building teams of teams. It's a great way to work together, see how you work together when you go after these really interesting technical challenges. So on that, I'd like to introduce and have Kurt say a couple words from BHP around their thoughts of Digital Tribe and this experience.
Thank you, Zane. To everyone that competed, I just wanted to say thank you. 2 weeks is long or short, depending on how you define it, but we know that it's been very busy for you. So Pat is one of the judges, an avid cyclist. I can't sit on a bicycle too long, I surf, and I was in Dongra on the weekend and got caught on the wrong side of a wave, and I just could not get to the back. And, you know, big board, get this wave on my head, and then the next one, and then the next one, and I'm turning around, and the shore is a lot closer than what the back line is, and I'm starting to think, yeah, maybe I should just paddle out and call it a day. And I'm like, oh, next week is work, I'm probably not going to get a chance. So paddle through, and eventually you get a bit of a break and you get out to the back. And I was sort of sitting there waiting for the next wave after just being pounded, and you know, there's a time you sometimes thinking, I was thinking about you guys and the work that you're doing. And that kind of like getting one wave after the other hitting you and like getting pushed down to the bottom of the ocean floor and coming up. It's a bit like when you're trying to hack hardware or write code, or these two things that's supposed to work together didn't work. It requires a level of resilience. And that made me think that, you know, we do a lot with Digital Tribes, but it's also like the digital transformation that we're doing at BHP. It's a bit like it works awesome when it does, and when you have the ride of the wave, it's just the most amazing feeling. And every now and then you need to have that level of resilience to be able to paddle back in and tackle it again. And that's what we want from the people that we work with, whether they are employees or contractors or digital partners that we work with in the vendor space. So thank you very much for the effort and staying committed. I hope that you've made some new contacts, learned something new, could add something new to your CV, and we really look forward to working with you, you know, over the next course as BHP keeps adopting more of the digital ways of working into our own ecosystem. Thank you, Zane.
So what happened over the 2 weeks? We took some photos. It was impressive the amount of hardware 3D printed work that went and happened over the week. We took some photos. We're going to have a collage. We're going to send it out later. But really impressive the amount of work and where the work happened. First off, we want to say a big thanks to the BHP mentors. Without their help and support and coming in over the weekends, being here late, being available whenever, it wouldn't have happened. So here's some great photos of them, and let's give them a round of applause. And also, surprisingly, we want to thank and say thanks to all you guys, to all the participants. These events don't happen with all you guys coming down. We always get a photo collection at the end of different participants to the event, and for some reason, the theme of this photo was like deep thought. So everybody's in really intense discussions throughout it. So we wanted to say before, you know, now you can relax and chill. And that photo is actually from one of our events in San Francisco. So that guy wins the chill award at the end. All right. And really, give yourself a round of applause. Without you guys and the participants, this doesn't happen. So we got an amazing panel of judges. They're going to be here giving you guys feedback, asking questions. Jake Stride with the Digital Tribes in BHP, Kirsten Rose, also with BHP in the low admission side, Pat Burke, the general manager of Wellback and BHP, and then Matt Tui with AWS. So it's a good panel. Be ready for some good questions. So just quickly on the challenges. Challenge 1, can you enable operational awareness on civil equipment? And then challenge 2, which you guys probably know about, can you design a prototype which operates in an ad hoc network? So 2 really good challenges. You're probably up to here with challenges, so we'll quickly move on. There's some prizes. So we know that there is a paid engagement with BHP. That prize will be announced at the end of next week, not tonight. But there's 3 prizes that will be announced tonight. So through the judges' results, be announcing a first prize, second prize, and please keep notes on what you think is the best prototype, what you think the best presentation is, because you'll get to vote at the end, and there'll be a People Choice Award. So this is the pitching order, minus the first team and second team switching. Okay, so Digital Eyes is up first. The way that the pitch sessions will go, you will get 7 minutes, and then you will get clapped off. So very nicely at 7 minutes, people will say thank you, no thanks, and you'll have to stop. And then there'll be 5 minutes of Q&A. Okay, we're going to go through this quickly. We're going to take a quick break, dinner maybe not, but we will take a quick break and then get back to finish up the rest of the presentations. The ones that are in stars here are international or outside Perth. All right, so to welcome up, and just for your presentations, make sure you're ready. The transitions between the 2 teams, we do not want to take forever. So have your computer ready to go. Bring it up here. We'll plug it in super quick. Again, HDMI or mini display port, you need to be ready. Let's welcome up the first team, DigiEyes.
And we're live, cool. Okay, well firstly, thanks guys, thanks for being here. We are Team Digitize, and we're doing Challenge 2, so the distributed safety device working in ad hoc environment. On the team, we have a mix of mechatronic, physicist, mathematician. We also did have Jack, who was a web and mobile developer, but he flew out of the country, so I put a little plane there to signify that one. But anyway, let's hop right into it, and I'm going to hop right into a story about Jack, because he's not here and I can do that. So Jack is a BHP employee. He works on mine site, open pit mine drive for dozer. But just the other day, he had a near collision with another dozer on an intersection, right? Sorry, what's my train of thought? So the other guy blamed Jack, and so of course when it escalated up to the supervisor, he wanted to know what happened, but guess what? That also wasn't a simple process either. Yes, they had GPS data, but it was mixed up in vendor packages, and it just wasn't easily accessible, and the whole thing just took longer than it should have. So that story kind of brings up two things. What safeguards are in place for these near collisions between vehicles? And two, why should BHP have any hurdles to overcome to access their own location data about their own equipment? And that's where we come in. Introducing Digitize, a self-meshing wireless framework that alerts drivers when vehicles are close together and pushes that data directly to a BHP system. So how do we do this? Well, we did it in two parts. And the first part is a family of nodes that sit on the trucks or light vehicles themselves. The nodes are powered from the truck directly, so power is reliable, and we've done that using a cheap off-the-shelf voltage alternator, and using cross-correlation between the Wi-Fi nodes. I know where the truck is at all times using the Wi-Fi signal strength. In the design, there's also a battery that trickle charges the truck, so that when the truck turns off for storage or maintenance, it reports the last location of the truck back to the system. And this second half is my favorite one. This is the plug-and-play USB node that I've got here. So you plug this in, it powers directly from a local BHP system. Within 30 seconds, the server is ready to go, part of the mesh, and ready to push location data straight back into the local BHP system without any modification to the BHP laptop or server itself. Anyway, that's enough of me babbling on. Let's look at a totally not live demonstration of how this technology works.
Cool, so we did a little experiment during the day. What we have is a receiver, which is right here with the LEDs, and a transmitter device where I'm standing further away. And we have two LEDs that light up whenever the transmitter device gets within a certain distance. So the green lights up within 5 meters, so that's now, it's hard to see, I'm sorry. And the red one lights up when it's within 2 meters, and you can't even see that at all. But we did this at night as well, so at night time, the difficulty is actually seeing the person. So we're walking over at a similar pace, and you'll see the green LED light up first, followed shortly by the red one. Now, what's actually happening? The one with the Raspberry Pi with the LED is calculating distance, and it's finding the distances of all the Wi-Fi sources in the area. So yeah, it finds the one with the shortest distance, and if that's within 5 meters or 2 meters, that LED lights up. So we'll talk more about how that works.
Okay, so our solution was we created this ad hoc network of Raspberry Pis which communicate via Wi-Fi. There's also routing performed between the nodes, so even if they're out of range directly, they can still transfer information. And this is this CJ DNS, and that can also encrypt your communications. Each node in this mesh network is calculating the distance to the other nodes via the RSSI signal strength, and this Friss equation is the formula that we're using. It works reasonably well in open conditions with about 2 to 4 meters accuracy. The Wi-Fi strength on the Pi, so you have about 50 meters of range, because that's the strength of the Wi-Fi signal on the Pi, which can be improved. Each of these nodes is going to be sharing its distance with the rest of the network, so each Pi knows its distance to all the other nodes, and it will also know the distance between all the other nodes it's not connected to. And it can use this to trilaterate its position in 3D and get like a relative topology sort of all the nodes on the line side. And they don't actually have to be directly connected via Wi-Fi, because it will be done through routing, through CJ DNS. Just to emphasize, this requires no special setup. You don't need base stations. It's easily performed on Pis, very low power. And yes, it gets about 2 to 4 meters accuracy, which is better than the GPS solution. So I'll pass you over to Andy or Austin.
So the really cool thing about this solution is that BHP or whoever uses it can decide on the alert that gets sent to the person who's within a distance of near collision, and it can determine the distances as well. So in this setup, similar to the experiment that we had. Green light indicates that it's nearby, but not necessarily critical. And the red light indicates when there's a near collision and something really needs to happen quite quickly. So you can choose the kind of alert that the driver, let's say there's two vehicles, you can choose the kind of alert that the driver gets. Say for the green light, you can just flash a light within the dashboard of the vehicle. And then if it gets too close, you can sound some sirens or shut the machine down. That's for VHP or whoever's using this to choose. The other cool thing is, as Swaddle said, it's quite easy to use, quite plug and play. So this can be used not just for VHP's mine sites, but mine sites across Australia and either even oil rigs or other locations where there's not a lot of Wi-Fi access and no networking.
Just say a few words. So look, a lot of blood, sweat, and caffeine did go into these 2 weeks. But if we had more time, there's plenty more that we have that we'd like to have in store. We want to test field. We want to do field tests. We want to test this system with dust, with humidity around, which would be present on site. We want to upgrade the hardware, try better antennas, and I've only got 5 seconds left. So into industry partnerships as well. Thank you very much for Digital.
Cool. So we've got one mic here for judges, so everyone can hear what you guys are saying. Free to pass it out.
Hey guys, pretty impressive stuff, right? 2 weeks.
Thank you.
Well, congratulations. Seriously impressive, so well done. The question I've got for you is the range. It took about 2 to 5 meters. SME equipment, surface mobile equipment, typically we have a 50-meter exclusion zone. And when it breaches that 50-meter exclusion zone, that's when we want to know about it, not 2 to 5. How does that scale work with signal strength and the network in which it must mesh into? Can it actually be scaled to that point?
Yeah, so that's right. Those Raspberry Pis are actually quite easily modified to have a stronger Wi-Fi signal, and that will extend the range of the Wi-Fi network. But by sort of default, these ones have about 50 meters range. So it'll actually be able to detect something within 50 meters at least, and there's about plus or minus 2 meters there. So does that answer your question?
Yeah, it certainly does. So it's in that range.
Yeah, that's right. And it's easily expanded to larger distance with better antenna.
And just to add a bit onto that as well, to be completely honest, we should have done tests like that, but we were quite rushed at the end, so we just kept it at 5 into just the video.
So did you do all this last night? It's like a uni exam.
Yeah.
That's my recollection of uni.
The night video was last night and the day video was this morning.
Actually, already worked that out.
You're wearing the same clothes, we hope.
Yeah, so my first question was, did you have fun? Absolutely.
Yeah, we did have fun, and also great help from Solver as well, 3D printing all that little parts. So.
Awesome. So, I was just interested in kind of following from some of Pat's comments around how would you see this working, kind of on a big truck? Like, does the truck in the middle of your sensors cause you problems?
Yeah, no, so that's a good question. What we use to display the signal is just this crappy LED that we got from Ultronics, but really that's just a digital signal that could come into a little alert on the truck, and then when it reaches, say, the 20-meter range or something like that, then a small siren could be going. So we don't want it to overtake what the guy's doing and what he's driving. It just serves that reminder of that. In terms of the Wi-Fi signal strength, maybe do you want to talk a little bit about that one?
Yeah. So the idea is that you would also mount several of these per truck, because I mean they're going to cost $5, right? So very cheap to deploy multiple Pis, and you can use them all together to work out your positions. So multiple Pis per truck, right, will solve that problem.
Awesome, that's good.
Yeah, great presentation. How do you think about scaling the, kind of the device management and maintenance of, one or more of these across tens of thousands of assets? Have you had a bit of a think about operationally what that would look like? And,
So I mean, at the moment it's just running Raspbian. So I mean, you could easily push updates. You could have a node which is like sort of an update server, and it would be able to route updates throughout the network. with the CJ DNS. So I mean, that's quite possible. Obviously, if you maybe upgraded to a Raspberry Pi 3, which is just a bit more powerful processor, maybe a bigger SD card, it can store more information, but it seems to be fine with the Raspberry Pi Zeros.
And just to add to that too, in an operational sense, I guess, it would need some sort of integration into the system if you wanted to put it, say, into the BHP corporate system. I know the IT is very kind of structured around that. So you would basically just need to ensure that there's some sort of integration there, and then also need to figure out the distance between the nodes too. So if these are if just you just got Raspberry Pis and they're 10 kilometers away, then obviously that's not going to work. So you might need to scale up to a solution where there are sort of base towers around the place. As long as they have it, then they will automatically connect and everything will just work.
Right, and last one for me was the mentoring side of it. What did you guys get out of that, and how did you kind of validate that this was a problem worth going after?
Yeah, I can say a bit on that if you like. We found the mentoring to be very effective, actually. They were available for questions. Austin asked a whole bunch of questions at the start, so we got a lot of extra information, things like the voltage swing on the trucks, that sort of stuff that really helped us guide our way into the solution. We were looking at challenge 1 for a little bit, but then went back to challenge 2 purely because we found it easy to make a prototype. But yeah, all the mentors were very responsive on Slack, answered our questions, and I think very effective. So I don't think it's a too.
All right, that's it. Good stuff. Okay. Alpha team, you're up. Come on up.
So we sort of powering the make sure it's got a prototype how is that you want to see something?
Yeah, I mean, it's a good front end.
So that's basically, yeah, like part of this one. Oh, no, sorry. Yes.
Yeah.
All right, everybody, we're gonna get started. Sorry for the tech check. We're gonna get going.
Okay, g'day everybody. Sorry for the delay. We had some technical challenges. We were originally supposed to be up first, so we decided to call ourselves the Alpha Team. We're a group of students who are wanting to be engineers, designers, and even a psychologist. This is us. We worked on challenge 2 for the past 2 weeks. Next year. So as part of working on the challenge, one of the first things we did was we pretty much spent the entire first weekend sitting down with every mentor we could find and asking them about the solution. We wanted to make sure we had a really deep understanding of why this was important to them. Some of the key things that we found out was that reliability was very important, was one of the most important things. Another one of the things we realized was that a lot of the stretch goals were just that. There was a core task that we had to achieve, and we had to do it in the best way we could. So we started looking at wireless technology to figure out how to broadcast the data. Some of the options we had were Bluetooth, Wi-Fi, Zigbee. We quickly rolled out things like Zigbee, mainly because we didn't have much experience with it. Bluetooth, because a lot of people have had a lot of trouble, especially the mentors were quick to point out that it was hard to work with. Wi-Fi became quite interesting. There's a couple of ways you can do Wi-Fi. You can set up a mesh network. You can start reading RSSI signals. You can just try a point-to-point connection. One of the real challenges we had, though, was with a point-to-point connection, you can't make that connection fast enough when you've got a truck coming at 60 k's. And again, this comes back to those discussions we had early on. What you can do, though, is you can scan every wireless device in your area quite rapidly, and we soon realized that it became possible to, it became possible to start to wonder if we could put data inside of the SSID. So that's the broadcasting beacon, and we're going to talk about that soon. We also rolled out RSSI. Again, a lot of the mentors were quick to point out it's hard to get that reliable. So it came down to Wi-Fi and what device to use. Again, we started looking at the Raspberry Pi. That's what we were given. The Pi we were given, though, it's $5, but it's not the easiest to source. What is easy to source, however, is an ESP8266. Most of you will know what this chip is. Essentially, it started off as a Wi-Fi modem that you could connect to any Arduino, but the community sprung up around it and realized, wait a sec, we can just put Arduino code straight in it, and a whole bunch of other things as well. So what we've done is we've got this device that I've actually prototyped on the chip to find out the minimum requirements we need. We also realized that we can connect the GPS directly to it. So a GPS and one of these consumes a lot less power when it's just broadcasting the signal than a Raspberry Pi doing pretty much anything. So battery requirements get on. We'll switch over to a tech demo now.
Hi guys, I'm Tom. We have a video thing just to see this object there in action. Okay. This demo should actually show basically. It should actually show basically if I go close to a beacon, a LED will pop up, which will inform me that I'm too close to a danger zone, and I should walk away.
But of course, we can do that live.
Yeah. Hopefully you can see this. But right now, my beacon is actually on the development board. Right there. And it is, I think Ben here has actually just unplugged it.
I am.
But basically this is going to work to me if it comes too close. No, it's not.
Yeah,
oh, there we go.
There we go.
It is too close. I'm sorry. The video is a lot better at demonstrating this.
We actually brought this here for the judges to have a quick play with.
Yeah.
So what you can find is set this up here, set that up there.
About the receiver.
Like that, so we'll show you that.
We wanted to work out what's the best way of actually sending an alert. As been said before, RSSI was sort of dismissed by the judges. And I'm like, okay, that's like fair enough, like they're good experience. So I was personally curious and I wanted to test it out. And so I'm sure like while it might not work really long range, it might be great for short range stuff. And we tested. Yeah, it's actually. Sorry for the poor camera work. I'm not the best swimmer. As you can see, the light turned on once I entered the room.
We have it setting just up there. So.
Yeah, it's just blinking right now. Just I think if you're a person, if you just have the light turn on, you might actually get used to it. But if it's blinking, so it's sort of like a warning, I think. The SSIDs, okay. Basically, SSID is your Wi-Fi name. We allow 32 characters to that. We can actually monitor and change that SSID in real time. So we can easily send a GPS signal. Actually, if you look on your phones right now, my beacon is transmitting the Wi-Fi signal. You actually see the GPS coordinates at 4. Oh. Okay. Yeah, I think Ben's best to.
So quickly about this SSID, there was two major parts to it. Okay, very. Actually, we're gonna. Essentially, we were able to split it into a human-readable ID and base 64 encoded data where we've got GPS time. Where to next? 3 future ones. We want to improve redundancy, expand the feature set, build mobile accessories. Okay, so redundancy currently it's an ESP connected to a GPS. What we wanted to do was we want to explore the possibility of connecting two ESPs to a microcontroller and a GPS. That allows us to start playing with mesh networking as well, among other things, which is great. Also, we've got a programming plot on the bottom of it. It's just a headphone code. So, okay. Sorry, guys.
So that looks like an awesome solution. I guess I'll ask my first question again. Did you have fun?
Yes. We learned so much in this challenge. It was actually winning is like nothing right now. I've learned so much about Wi-Fi modules. When I came into this, I just wanted to learn everything I could, make an ad hoc network. Like I've got my own ideas. I've been used to, but other not just to mining sites. You can use it for health, safety. Anyway, this is all offline. You can send alerts, and it's really neat, really long range. That's what I really got out of it.
So I love some of the comments and things that you made. I made some notes. I'm not going to say them out loud to influence other people that are still to present. I'm looking at our poster over there with someone with a hard hat on and thinking kind of the way that you've looked at this and low power. Like, what are some of the other solutions that you might see beyond kind of this space? It's nice that you kind of pivoted your thoughts.
Sorry, you're asking like what else we could add to this, or
so we can expand?
Yeah, look, I'm looking at a hard hat and going, one of those might fit on the side of it.
Well, yeah, so these ones here, these have actually been designed. This is two powerful magnets that Yaron was kind enough to give us. So essentially, you put a metal on the back of it. Low nuts, sorry. Bit of metal inside the
Sorry about my budget.
Yeah, understandable. So these are designed to be fitted on that, and we found a battery big enough that fits in that enclosure to go for 3 days.
These are great for beacons, so attached to the safety like devices. But for personnel and trucks, you can just use this and touch it like that.
Exactly where we were hoping to go with the rest of our presentation. Essentially, you can get something small enough, it's wearable, you put it here, on here, it gives the alert, pairs with your phone, gets the GPS from that. Yeah. Next question.
So one of the things I thought you guys did really well was kind of walk us through the logic of how you approach the problem and how you listen to your mentors. So well done. I thought that was really good. So I guess I'm interested in what do you feel like is the biggest breakthrough you had in terms of the technical side as you were going through it?
Okay, it was more like you got a problem, you spent about 4 hours on it, you solved it, got another problem straight away. This is hard. I reckon the biggest challenge, I spent 18 hours, like straight up, a step to 4. We were just trying to get the SSID to, like my computer to upload messages to the chip itself. It was just, there's a syncing issue, and then found it out in about 4 seconds because it was building the hardware, and I was in UWI and not at ECU.
Yeah, there was a period a couple of days ago where I was trying to make these devices from scratch, and I got to the point where it just wasn't working. So there was something going wrong with the hardware. I thought I'd let the team down and pretty much just killed our chances of success. I did figure it out though, and the great thing about that is as Thomas was saying, it allows us to keep building on top of each other's weaknesses and strengths. We start developing
and I think
how we can make it work.
It really enforces teamwork. I think as a team, we worked out so much more than I could have done by myself. Ben could have done by himself. Michael, just in the news, just saved the day like 5 times today. Like we couldn't get this thing to it, and the friend just looked at it and said, "Oh yeah, the battery's shorted." After we'd spent like, and it was it was a great team from everyone, and I think.
Just add something to what we've done as well. We actually tried to utilize the Raspberry Pi as well. So we thought about the GUI, or like graphical user interface. So we tried to utilize the Raspberry Pi that we've been given by you guys to do like a good job with receiving the signal, like the SSIDs, and see how can we do a program that can nicely print a message for the user, say please avoid this particular area. So we'll try to use this. It's kind of like a stretch topic, but we'll try to put in that stretch topic the Raspberry Pi beside the ESP as well, was kind of redundancy as well.
Yeah, there was a lot of the mentors were bringing up that they were going to use Android tablets. So mentors were saying they're going to put Android tablets in the trucks, and most of the trucks have all the technology we're talking about on board. Exactly. So we took our time and we focused on how do we make a fixed beacon and how do we make beacons for personnel as well.
Okay.
So one more question, comment, and we've got it next time.
I'll probably make a comment. One of the things I really like what you just presented was a personal safety device. Whenever we put people, real people, in the line of equipment with very limited vision, it always creates an issue. So you need to think about, this might be a small little device, but at the end of the day, when you scale this up and take it to market, it's all about saving lives. So fantastic. I really enjoyed that. Very similar question to I asked our first team. The range. Now, if you think about a mine site, you've got 50 trucks running around.
Okay, so
ancillary equipment, you have another 100 pieces. So you've got 150, 200 pieces of kit running around, all with limited vision, dusty conditions. How's this going to scale up?
Very, 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 very well. Very well.
I did this in my testing for the RSSI strength. Basically, me and my roommate just came from Sweden, and he just wouldn't want to see. So he was helping me out. He was like reading it all, and I just walked like every 8 meters. I ran out of room.
Up to 208 meters.
That's 208 meters, and I was actually kind of getting bored a bit, walking and staying. And that's a 208 meters radius, so you can like double that. If there's like a person there, and if you, because it's actually a Wi-Fi module, we could, in theory, as an expandable goal, make a connection between say 2 beacons, and that would then have the range of that to there and keep going.
There's also a YouTube video where those can, with an antenna attached, you can get up to 4 Ks range. And there's the exact same module with an external antenna. 4 Ks range, 5 Ks.
Okay, for the next one, we're actually going to run a video. This is a team that's from Melbourne, so they put together a pre-recorded video. We're going to play that, and then we're going to be able to talk to them on live stream for Q&As.
Adextra is an Australian-based company.
Ready? This is a team from Melbourne. This is pre-recorded. They're sitting on the live stream, so we're going to watch their video, and then George, who's watching by that camera right there, is going to do a live Q&A with the judges after this.
Adextra is an Australian-based company focusing on end-to-end solutions for the Internet of Things. We develop software to connect almost any data stream to the cloud, as well as a growing suite of tools for reliably managing network connectivity, including 3 and 4G networks, Wi-Fi, Wi-Fi mesh, and Ethernet. Most of the installations we deal with are unattended and incredibly remote. Some are even inside the Arctic Circle. But regardless of location, our platform provides resilient and secure communications with your devices for remote management, file transfers, and cloud-assisted processing, such as computer vision. Once your sensors, trucks, and PLCs are sending data to the cloud, you can get real-time updates with dashboards and visualizations. In this video, we will demonstrate the collection of data over a low-power 2.4 GHz mesh network. This type of network is great for both microcontrollers or standard Linux machines such as the Raspberry Pi. However, the major advantage of mesh networks is that each node acts as an entry point into the network, thereby continually extending the range of the network the more nodes you add. For this demonstration, we've selected the ultra-low power Nordic semiconductor chips. These provide up to 2 megabits per second throughput while keeping power consumption to a minimum, meaning that using these chips long-term on solar or battery power is not a problem. We hooked these modules into an Arduino Nano and a Raspberry Pi using SPI. However, you could also use USB. A link to the open source drivers is available in the notes. The primary feature we needed for this project was a highly flexible topology. It must support both dynamic and static addresses, and nodes must be able to be added and removed at any time. We selected a variety of mains-powered and solar-powered devices, including a wind turbine, a water flow meter, and a weather station. Here is a diagram of the final deployment. The topology is completely dynamic and self-configuring, meaning that any node can communicate with any other node in the mesh, but it may not always take the same path. For example, the solar-powered sensor may communicate directly with the Raspberry Pi. Of the nodes, one is completely solar-powered and all the others are powered by 5-volt adapters. The weather station is a commercial off-the-shelf station from Davis and is connected via USB to the Raspberry Pi. Overall, we're monitoring about 40 data points across all the different devices. These streams of data could be anything relevant to the safety network, such as GPS and NMEA data. The Raspberry Pi is running an Adextra agent to relay all those data points to the cloud for visualization and analysis. Here are some photos. For visualization and analysis. Here are some photos.
So who's been working on Wi-Fi networks the whole 2 weeks?
Photos of our setup. With the Undexter agent running on the Raspberry Pi, we have complete visibility and remote control of the mesh network and the data collection nodes over a highly secure link. The agent provides secure two-way communications with the cloud, enabling file transfers, remote shell commands, and configuration updates all in real time. Here's the dashboard we created for this project. The yellow sensor cards display live readings coming from the agent. The blue search cards enable you to view historical data, and the purple analysis cards enable advanced features such as evaluating formulas based on live data. Here we've set up a basic formula to find the temperature difference between indoors and outdoors. Taking a closer look at the search interface, you can see all the latest raw data points being collected and quickly create visualizations. And finally, there is the management interface, where we can check the status of our Raspberry Pi, transfer files to or from the Pi, update the data collection configuration, or manage our digital certificates. Other benefits also include seamless metadata management, scheduled reporting, alerting, and optional on-premises hosting. Looking to the future, further investigation into 802.11s hardware is required, and we're looking for ways to leverage DNS for ad hoc service discovery, such as automatically connecting mesh networks to the internet via any node that is in a Wi-Fi or mobile coverage area. We are continuing to improve the design of our 24/7 solar-powered Pi, and we believe that in combination with mesh technology, we will continue to push the boundaries of resilient remote data networks. Thank you to Unearthed and PHP for allowing us to take part in the Digital Tribes Hardware Challenge.
Just give us 2 seconds. We got to join them up on the webinar. Sorry about this. We did have it tested, I promise. And this is the tech challenges that come through, including the Wi-Fi. Just to be ready for the teams that come up next. So team 1776, you guys will be next once we get this working. We might actually delay this Q&A just to make sure that we get it working, and then you guys come up first. All right, so let's do that. 1776, come on up, guys. Let's get through that presentation. We'll do some Q&A, and then we can go after it.
Hello. Ready?
All right, guys, keep going.
Everyone ready?
Yeah.
Okay, guys. So let's see. We're Team 1776, hoping to bring a revolution to how BHP does mining. Chose 1776, American Revolution, or more friendly. We know exactly what we're doing. So probably the first thing you noticed is our little Raspberry Pi setup, done with duct tape, not 3D printing, because real engineering something with duct tape and cable ties. Okay, the other thing you'll notice is that we have cameras on that thing. Why? We were probably the most ambitious team, I'd say, being like one of the only teams that decided to do challenge 1. Okay, so our team. We got thrown together at the start of this hackathon. We were lucky enough to get a pretty diverse. I'm a biomedical engineering graduate. We have Michael, who is a software architect inventor, and we have Yihao, who is a PhD mining engineering student. So a nice range of experience there. And with these two guys, it's their first hackathon, which is awesome. I've done one previously on it, so it was good to meet you people. Cool. So, tackling challenge 1, operational awareness. From the get-go, a lot of people saw this challenge and went, what does that mean? And that pretty much put them off from the get-go. So for the first week of the challenge, well, the majority of the first week, we really looked into finding what the core issues with this problem were. We looked online, we talked a lot with the mentors, we talked to each other, talked to people around the place, and basically boiled this down to one core focus, which is we've got these great engineers in the office producing great 3D maps for your graders, you know, all this point cloud data, all this work put in, and then somehow it goes to the operation and gets lost. You know, it's just not being transferred. You know, it's just the operator goes, get a 2D image, and I'll do my best. You know, and then of course the reverse cycle of that, which is you're waiting this massive delay for an external company to do drone flights to then get a massive data you don't really need. You just want to know if the road's right, and then it's coming back, and you got delays until the engineer goes, well, we're off, so now this cycle has to start again. And it's just so slow. So we thought, what can we do to help fix this cycle? So what was our solution? we came up with what we call Root VM, which is basically a data cycle system in two parts, one for connecting the engineer design to the grading operation, and the other connecting the grading operation back with the quality assurance for the engineer. And with our solution, I'd like to hand you over to Michael.
Okay, we've got a phased approach to the solution here. I said we've got those two goals. We've also put in a value web for further development and things that can be leveraged from this technology. There's a lot of potential in there to simplify and streamline your mine site operations. So the first implementation we're doing is simply a screen in the cab that gives a point of view, an operator point of view for the design that we're building, and some cameras that are mounted to do stereoscopic mapping in an off-board delayed fashion. Second phase is to possibly go for a HUD display and do the mapping, actual surface mapping on board the vehicle as it's working. And the third future one is to actually integrate two displays with perhaps an augmented reality display for the operator. The next one. This is basically a mock-up of the first deployment, where you've got a screen here which is showing the 3D view of the plan data from the operator's point of view. The operator sitting in the cab looking out of his window, and you can actually correlate the landscape, and these lines are giving some indication where he should be doing the grading. As this solution grows and gets more sophisticated, and we're able to incorporate the real-time surface scanning information in, this display we hope will be up here as a HUD, so it's actually overlaid on the landscape, and it will be color-coded to tell the operator where it's right, where he needs to put more dirt, or where he needs to take dirt away. So by the time he's finished this, it's right. And none of this rework cycles and coming back and doing it again and again. Yeah, the next one. Back to Robert, the next one, I think.
Cool. So that we were explaining there was our Root VM display, so our forward mechanism. Now, how do we get back? Well, that's our Root VM vision system. So we brought in those Raspberry Pis, which is what we've been operating with at the moment. We know there's other technologies out there, but we thought we've got this vision. Here's what we've got to do in our 2 weeks. Here's what we can do in 2 weeks. And then we also have a plan for what can we do in the future. So here is we've taken our Raspberry Pi stereo vision from a generic road, which is actually the e-house street. So good thing he's got, no house information. Anyway, and we've taken that in, we've processed the data on the Raspberry Pis and then fed that back to an external laptop to generate our 3D mesh, which from these, the idea of that is we can then eventually onboard real time from that mesh, measure gradients, because one of our problems we identified from the mentors was that immediately there is a safety hazard with if some of the graders or other machines are operating at the wrong inclines, can be as little as 10%, it makes a massive difference with massive trucks. So yeah, that real-time feedback would be the optimal for protecting operators, as well as real-time just, again, gets rid of the delays. Best part about this system, we thought, is that you immediately can just cut out the drone flights. You can take this, strap it to the back of your grader, on his final run, switch the on switch, take the video, generate the map as you go, and there's just not a delay. And it also gets rid of that dependent on an external client. Cool. So that's our product. How do we actually get there? So after doing a lot of hard engineering, sketching, revising, coding, looking at options, looking at budgeting, looking at tech that's already out there, we came up with our solution as we did. We did the groundwork for stereo vision. There are cameras out there. A lot of people have heard about the Z camera, about $600 bucks per unit, another couple of $100 for the software. Major problem, cameras are too close together. This one, we're able to actually, with the knowledge we gained in the background, we can actually fit it to a grader if we wanted a higher separation, which is what I was talking to Richard about. Anyway, that also isn't limited to a grader. You can change it to whatever vehicle you want mapping your section. So the immediate payoffs for this would be stop paying for the drone flights. No one wants to do that. We can start constructing accurate roadmaps a lot faster. You want that turnaround time, and especially if it comes to identifying hazards. We've got fast quality assurance. And then, of course, we have a list of longer-term goals that Michael will talk about on the next slide.
Okay. Basically, this is the area we've been looking at. there's a lot of stuff we can do down here with the cleaning up, the real-time verification to make sure that the road's been built properly. We can give you a temporal surface database. When we take one of these scans in real time, we can attach a timestamp to it. We can then take all the timestamp scans and stick them into the surface database, something like an Elastic database, so that you can then write a surface stamp composition tool that will take a date and a location, go into the database, fish out all the scans and build up the current surface profile. And you can also go backwards in time to see what the previous scans have been for that area. And this lets us do something like automated age inspection. So we can have
Q&A.
Did you guys say one?
Yeah, we did. Okay. Yeah.
Oh, okay. Again, are we on? Oh, now. Okay. Again, fantastic, amazing. Right? You didn't quite get to tell me how the camera works, how it scans, how that information gets transferred through, and can you actually get it on our equipment? If you've ever been on a grader, it's not the smoothest bit of kit, right? Yeah. It's all over the shop due to the nature of the work that it's doing as it cuts through the road. So I'm pretty keen to understand that little piece around how you're actually taking the data from this camera, how that is actually physically working.
Yeah, obviously we know there's a big difference between the lab environment and on site. That would be our next step in terms of creating a more robust rig, and also there are other options in terms of if you're using optical or infrared or LiDAR and that sort of stuff. For this prototype, we're working within our budget of the Raspberry Pis and $60 we got given, but we have looked at those other options. We have a bunch of files that we have submitted of research that we've done. So if people are interested in this, we can go back. If someone comes in with a different idea from the Digital Tribes or from the Hardware Tribe, that's good as well. We have done research. At the end of the day, we chose optical because it's what we could get done in this 2-week time frame. But otherwise, in terms of processing speed, we've got information on different processors, Raspberry Pi Zeros, we've got PiCams that are affordable, and that's pretty much what we can do in our time frame. But yeah, we do have plans in terms of we'd like to really talk to the operators, get a feel for the graders, because we're not miners ourselves, we're not grader operators. So that's our next step in terms of field testing.
In terms of actually computing the stereo images, we need pairs of frames that are taken at the same time from 2 different cameras. If in one frame they're oriented like this, and in another one they're oriented like this, that's not really a problem. We can still calculate where the surface is. And we've used shock absorbers to mount the processing unit.
Awesome outcomes. Well, I love the fact that you kind of managed to look at it from both sides, not just kind of generate the data, but also kind of showing how it can work to operate as well, which I thought was really good. I'm just interested on your thoughts around kind of the range and the detail of the stereoscopic image and the point cloud that you generate off it, of what the distance is and how sensitive it is to movement as well.
So at the moment, our point cloud's running, we pretty much take our still images because that's the benefits of working inside a lab. But otherwise, you sync that with a GPS stamp, and that's what Michael was going to at the end in terms of getting a real-time map. On board, depending on your processor speed, if it's just Raspberry Pis, we just store it and operate on a separate computer later, which still eliminates that drone flight need because you've got the data with you. If you need it quick, you just get someone to express it and deliver it. Otherwise, in terms of actually, I've gone off on a tangent. I'll let Michael continue.
Yeah, what we're actually getting from the Raspberry Pi is streaming video, running about 5 frames a second. Each frame is probably going to get probably from there to there, and we just stitch them together one after the other to make up a continuous surface.
Yeah, really great solution and presentation, guys. I particularly like I guess the practical nature of thinking about the time frame, and also thinking about what could be done now and incremental improvements would be factored in. The question I've got is, how would you go? I mean, you can clearly see a better feedback loop here and an opportunity, but how would you go about quantifying the actual performance improvement at a site through implementing something like this?
You could measure the reduction in the cycle time to get the roads approved between when you first design a road and when you finally finish doing it. You could measure the cost saving on that cycle. You potentially are looking at a scenario where you're actually moving up to just-in-time grading, where you're going to grade a road just before it becomes unusable. Again, that would lead to a reduction in the costs of fuel for the haul trucks and maintenance on the haul trucks. Some of this stuff's fairly hard to quantify because it's letting you do completely new things, like the 4D playback, where you can actually have a look at exactly what a grade has done on each pass that it's made. Be used potentially for training new grader operators.
Thank you.
Any more questions? We're good stuff. Okay. All right, so we are going to give a second go of our live Q&A. We now have them streaming. The Wi-Fi is not acting up as much.
George, can you hear?
Yep.
All right. You guys got a microphone as well. So George, just give us a quick recap of your presentation, very short, and then, as I said, ping a few questions to the judges your way. Otherwise, the judges may have a few questions from their pitch, what you just presented. So go ahead.
Okay, so what we worked on was to try and get the mesh working. We wanted a true 2.4 gigahertz mesh working on anything from a microcontroller to Raspberry Pis. You have developed Raspberry Pis. We use a lot of Linux devices to monitor all sorts of equipment. And what we wanted to do was make it as reliable as possible, because we know that when these devices are out in the field, you know, it's usually unattended, and people need to make sure that it's reliable as collecting data. So we focused on that aspect of it. We were thinking it in the early stages to work on challenge number 1, because we've also done a lot of work with computer vision. In particular, we've done a lot of work with recognising faces and face recognition, face detection with our IoT stuff that you saw. And we thought this would be a good solution. We were going to put that part in the challenge too, but we just ran out of time to do it. And that's why we focused on the mesh aspect. And we wanted to show the mesh working, you know, over a distance of about 100 metres. We tested it out over 100 metres. That solar station that you saw, the solar powered node, worked up to 100 metres. And it was really interesting because sometimes the data would go through the relay node and sometimes it would come direct to the Pi. We're actually going to use this mesh in an agricultural solution. We've been talking to some people over the last few months to do it, to look at soil moisture and canopy cover, where we have a large array of these devices. We've already got Pi and Linux devices out in the field, like we said, working 24/7 solar powered. But we're really we're looking at making these meshes as reliable as possible. So that's a recap of what the team at Artextra has done.
Great. Hi, George. It's Kirsten Rose here. Thanks for that. Your presentation was really, really smooth and polished, especially for being remote, so thank you. But I'm going to give you a bit of a hard time because I'm pretty sure you didn't tell us which challenge you were working on. So unless I missed it at the beginning. So that's one thing just for future reference. I think you need to be pretty straight up about that for some of us who aren't maybe as technical.
Sorry, you have to speak a little bit slower because it's just breaking up. Skype is just breaking up.
Sorry, is that a little bit better?
Yeah.
Okay. I just said, unless I missed it, I don't think you told us which challenge you were working on in the presentation. So it took me the first few minutes to make sure that I knew which one you were working on as somebody who's not super technical. So that's just a little bit of advice for next time.
Sure.
I guess what I did miss, or what didn't sing to me, was how you were contributing to solving a BHP problem. So I understood the technical aspects, and I understood you were very, I think, clear about the solution. But what I missed was what aspect of our problem you see it solving.
I guess, yeah, look, perhaps I didn't make that clear, and what we focused on was, and we talked to some of the people, Sam and Yaron, I think, at the start. We also talked to some people that worked in, some people in Downer, and some people that worked at BHP in other areas. I guess we took because we had limited time with this challenge, we looked at from a technical aspect point of view, we saw what's the biggest risk in all of this, and from solving a challenge of having these distributed safety devices everywhere, where you might have, like the other teams had, where you had a little GPS nodes or nodes that work on radio to try and get co-location, or even the computer vision stuff that we were thinking of doing. We saw the biggest risk to this as the mesh aspect of it, the communications aspect, where you've got a large mine site where you might have hills in the way, where you might have big lumps of metal in the way, in the case of big trucks, and so we focused on that aspect of it. And that was a bit of an assumption on our part to work on that, but so that's how we came about to that, working on that. And that's why we focus on the mesh, I guess is what I'm saying.
Can you hear me okay? Is that slow enough? My link?
That's about right. That's about good.
Cool, awesome. So look, I was just after a bit more information around what was and wasn't done in the challenge. It felt to me when I saw the presentation that there was kind of some pre-existing work there, some parts that you'd used already. So could you give me a bit of background around which bits were done specifically for the challenge?
Sure, yeah. So the IoT stuff, the Internet of Things stuff, where we've got the agent and the cloud, we've developed that over the last few years in our business. Where we spent some time on this working was the mesh, in particular those chips and making them as reliable, and working with a Pi, working with that, and just looking at different. We tried the Batman implementation of 802.11s, which is the open standard for mesh networking. So we worked on that aspect of it, and we worked in connecting in that in particular that solar powered sensor. We worked on that as well. The actual, existing talking to wind turbines and weather stations, we've already done that. We've done that for a few customers. We've done that on a big scale as well. But the mesh aspect of it, we saw there was a lot of overlap with this, and we wanted to work on that as part of this challenge.
Cool. One more question? Go for it, Pat.
Yeah, thanks. And again, a lot of work. It does look like you've developed this over many years, but what's the limitation?
The limitation, we connect a lot of machines to the net, and the limitation is the last 10 centimeters or the last kilometer. That's whether you're connecting via RS485, Bluetooth, mesh, as in this case, Ethernet, having something that can span a few kilometres, or like I said, 10 centimetres, and have it unattended and have it super reliable. That's the real challenge, and that's where we keep on working with it. We've tested all sorts of single board computers, from Technologic Systems, Beagle Bones, Raspberry Pis, Orange Pis, Banana Pis. I've got Amiga. We've got them all over the place here. The key, we had to develop our own image, our own Raspbian image, just to make the communications reliable, because you'll find that out in the field, it'll work for 1 or 2 weeks, and then the native network manager will just fail to reconnect. So we've spent a lot of time on it. This is the real challenge aspect, to make it super reliable. We've developed around power boards around the Raspberry Pi, so we have a solar installation. The power board will talk to the Pi and the Pi will say to it, turn me off and turn me back on in an hour or something like that, so that we've got a backup system in case something goes wrong. So that's the real challenge in all of this, and that's where we keep on working with it. Yeah, so that's what we found over the last couple of years. We're only still a small startup, but we've spent a lot of time making, like I said, in the presentation, some of our installations are in the Arctic Circle in hydro turbine stations in Norway. There's no one out there, and it takes 3 days to get out there on a snowmobile, like train, plane, and a snowmobile. So we've got to make it super reliable, and that's where a lot of our stuff effort is going into.
George, we'll have to cut it there because we have to move on to the next team, but thank you so much for coming in, tuning in. Cheers.
All right, we're Team Safety Net, and we're tackling the decentralized safety network challenge. So I'm Tom McCreary. I've got a background in engineering and finance, and this is Greg.
Yeah, I'm Greg. I've got a background in computer science, networks, and distributed systems.
So first, what's the current problem with the system that's currently in place? And talking to the mentors, we're hearing that it's a very manual process, and it's really dependent on awareness and compliance by people. And there's no real audit trail around if there's something happening or you're getting close to a risk that you can proactively target where to improve. So our solution, we're looking at empowering the operators with digitally enhanced safety awareness. And we're doing this in an environment where there's no traditional communication infrastructure. And we're extending the traditional methods of the cones and barricades. We're not kind of revolutionizing, coming up with something completely different. It's just kind of incrementally improving upon, just making it that much better.
So yeah, we'll move on to a video that we made earlier.
Hello, welcome to this demonstration of Safety Net Smart Code. Safety Net Smart Code, a regular warning code, has a safety net device based on the Raspberry Pi embedded within it. In addition, has ultrasonic sensors mounted on the code. The safety net device communicates with all other safety net devices in the network over ad hoc Wi-Fi. The way in which the safety net code works is that when an object is detected within a predefined distance of the code picked up by the ultrasonic sensor, an alert is sent to all other safety net nodes in the network. I'll just give you a really quick overview of the safety net code. As you can see, it's really code. The only difference is that up the top here we have a simple ultrasonic sensor mounted on the code, leading into the Raspberry Pi device within the code. Now, because the transmission range of these Raspberry Pis is actually really impressive, in order to set up the network where the communication needs to travel over multiple hops, we need to cover quite a large area. So I think we're going to need to take to the to show you our experimental setup.
So what we're seeing here is the camera situated down there, and off in the distance here is the very first node that we're trying to connect to. There's quite a big distance there, but then off in the distance again is the next node which has got this device on it. And we're showing that our system can do a multi-hop scenario, so anything that's connected into this network, even though they can't see each other directly.
So now I've got the network set up. Node 10.0.0.1 is the furthest node and should not be in direct communication with this device here, so I'll just ensure that that is the case.
This is just us doing some testing, it's not the interface we expect.
Now I just started up OLXR daemon on this node, and we can see hopefully that node 1 is now accessible, but only via node 3, so all communication will go on an additional hop via the cone in the middle. Now what I'm hoping to demonstrate is I will go and encroach upon the safety barrier in cone 1, and we should get an alert on this device. Okay, so the green circle on the right of the screen shows that there's no current safety alert.
This is another way of
proceed up to the file barrier and go within the predefined distance. So hopefully we'll get a red alert showing up.
So we've also since kind of had some additional ideas of how we can provide that alert. So if you go into there and you get the red signal, we've also got a device with a little display on here that'll come up and say, something's gone wrong, contact someone, which radio channel to do that contacting on, and I'll just keep cycling and finding that. Yeah, so the goal of our devices, we're targeting $100 per device, and we've used the Raspberry Pi as the prototype, but we haven't locked it into being a Raspberry Pi. So we're focused on being an open and vendor-independent standard, and some of the things we've been using are like the Raspberry Pi, Python, Linux, Wi-Fi, and so on. And the power we're seeking to get out of this is about 80 hours. So that's using a 16,000 milliamp hour battery at about a 200 milliamp hour draw.
So I think the other competitors have also spoken quite a bit about ad hoc networking, so I can probably get through this really quickly. The key point is that in a traditional infrastructure-based network, you rely on an access point, a backbone, backhaul, both things that can fail and are not typically deployed on sites. Our ad hoc network is completely peer-to-peer, doesn't rely on any infrastructure, and has multi-hop communication, which I'll also just go through really quickly here. If we have one device with a 200 meter radio transmission range, we've got another device that's outside of that transmission range. What multi-hop communication gives us is that with another device in the middle within communication range of both the other nodes, the communication can hop over them. Sorry.
So we saw in the video the example of the cone with the ultrasonic sensor on that. We've since been thinking of how we can extend that concept. So we're thinking of an idea of permission zones, not warning zones. So we pre-programmed whereabouts we're allowed to go. So for example, you might not allow a dump truck or a haul truck to go into an area where you're doing some drilling. So you'd set that up as an area that's unsafe or unallowed to go into. And then each device would have a trigger, or we'd talk to a code in the area. So it has to get an authorization or a permission to enter somewhere. So if the network is unreliable, which we've seen a few examples of the internet tonight, it doesn't allow you to go in. So it fails to a safe world. So it's safe by default.
I think we can just maybe go into another video again. We've got a bit of time.
Through our safety net truck here. Have a GPS antenna up here. Connected through the Raspberry Pi, connected to a power supply, which is where the type of conversion. The Raspberry Pi Zero runs our safety net software, which communicates with other safety net nodes via a passive protocol. Messages are sent via UDP multicast and multi-hop communication enabled. This means that we have communication range of several hundred meters up to several kilometers without any need for physical networking infrastructure. Here we have a safety net node running on a simple Windows laptop, having our positional awareness for application. Picked up one other safety net node. We just remote it here. It's a sticky truck over here.
And we're just showing how it can communicate and as it
Yeah, so sorry, it was showing the positional awareness, which the location is transported over ad hoc. It's picked up by the GPS.
Cool. Questions?
Questions?
The possibilities are endless when I look at this type of technology. It looks really well polished for 2 weeks as well. Did you do it all in the 2 weeks?
Yeah.
Was that a genuine yes?
Yeah.
Yeah.
I can give you the code.
I wouldn't know where to start. Active mining areas. Do you think you'd be able to scale this concept to a personal device, a personal wearable device, so it would potentially warn, so like a two-way, you've got one signal here that a reader's reading, assume you could have a reader wherever, or multiple readers, but if a light vehicle or an individual was to inadvertently be in an active mining area, this can pick it all up.
Yeah, I think the hardware that we use in the challenge, the Raspberry Pi Zero, it's so compact
and it's so powerful. We really enjoy working with it. And the possibilities for adding additional sensors. We use an ultrasonic sensor in one of the videos, which has a 3-meter range, which is pretty close. So for a sort of a more close proximity warning system, which I think is what you were asking about, it would work really well.
I'm going to make your eyes water here. 2 weeks ago, just in the process of deploying a GE system for a fleet of trucks. $5 million worth is the cash that went with it. How much did you say this is worth?
We can talk later.
The shade under 5 million.
Is that stronger than the gear?
So this is not technical. Did you guys meet in this process?
Yeah.
Yes.
Okay.
Yeah.
So what? Again, I would ask the question I asked before. What was the biggest hurdle you had to overcome? What was the biggest stumbling block in the process over the 2 weeks?
For me, it was children.
Then we got the truck.
Yeah. I got 2 girls out to borrow it.
All right. Okay. Oh,
Yeah,
girls can have fun.
I think it was just time. Personally for me, just challenge. Obviously, there's some technical challenges, which I think are well understood. You know, we all face the same technical challenges, but I think finding time in your week to kind of do a bit extra was, for me, the greatest challenge.
And for me, when we were trying to test the multi-hop testing in here, we found it really difficult to get 2 devices not being able to be within range of each other in this whole facility. So we're trying to struggle, like putting it in the far corner of one room and in the far corner of another room, and trying to figure out if they're going to be in range or not. So really quite impressed with the range of these devices. Cool.
I actually have no technical questions because it was a really good presentation. Like for 2 of you in 2 weeks, just amazing kind of what you've done. And I also kind of love the way that you thought of a whole different number of scenarios, like you've waterproofed your unit to go in a truck and you kind of attached additional sensors and actually done it with a witch's hat or whatever they're called here as well. So yeah, an awesome presentation. I kind of felt it touched both the kind of story business side of things and the technical piece as well.
Yeah, to echo that, really enjoyable. Love the little screenplay as well. It was quite engaging, quite scrappy, which was good. I picked up on one little detail which I'm just keen to explore is the first demonstration when you approach the furthest witch's hat, there was a little latency in the green flag turning red. Is that genuine network latency, or is that a tuning thing with the device, or what are your thoughts on it? You don't want that to be a difference between a hand and not having a hand.
Yeah, I mean, great for picking it up because it's an experiment. Actually, it only took 1 take to get the demo to work, which I was surprised about. I thought I did a few times. So that bit where you saw the slight delay, yeah, I didn't investigate it further, but I did notice it in the video. The network delay that we get on the multi-hop is actually is not significant. I mean, that's in all the testing that we did. We did quite a bit of testing outside of that. So in terms of that delay on that particular shot, I don't have an answer. Yeah, I did notice it, but I hope nobody else would.
Good stuff, guys. All right, we got one more presentation, then we'll have a quick break. So one more presentation before that.
All right, hey everyone. My name's Alan. I'm from Digital Lighthouse, Team 4. We decided to do Challenge 2, the ad hoc networking. So I was lucky enough to have 2 BHP employees. I've got Anthony and Ibrahim. Ibrahim's GIS and Anthony is IT. and I'm a control systems engineer for GE. So we were lucky enough to have access to some PHP employees. We had geotechs, blast engineers, just for getting some consultancy on hazards that exist in site and how we can improve it. That's it.
So imagine yourself on a nice hot day, turning up into Newman, just got off the plane, and site's obviously changed since you were last there. New hazards have appeared, etc. And you want to know what new hazards have appeared. So as you can see, I'm not really holding any tech at the moment. There's no box or whatnot. You just take out your phone. You join to the network. You click and go, which basically brings up a map showing you where all the new hazards are and all their exclusion zones. Then you're wandering around for the rest of the day, and you get in your live vehicle, and you've said, all right, it figures out you're in a live vehicle, and you've selected that option, and you're driving around, and suddenly you get this alert on your phone saying, wait a minute, I've just wandered into a blast zone, the blast is at 2 o'clock. Oh, and not only that, the blast engineer or the blast controllers have also got a notification to say that you've entered that zone. So they can now contact you. And as you probably, or BHP people will be aware, on the 3rd of July, at about 2 in the afternoon, we had a light vehicle at Jimble Bar go into a blast zone, which is pretty serious. Obviously people can get killed. But our tech can be used for a whole stack of scenarios, including working at heights, isolation points, and the more you explore it, it can actually be used for a lot of the production type activities as well. So what does ours look like? So this is a picture of a blast. And as you can probably see, we're blowing up Perth. And you can see that there's a couple of markers there, GIS markers. The red zone there shows you that there's going to blast there. This one is an exclusive sort of working area, that kind of thing. And as you wander into each one of them, they will actually give you an alert to your phone. Okay, just team working, just quickly on that. So, though I did know of Ibrahim, we've never really worked together. Alan, we only joined each other on the day. And on the day of the challenge, we caught up with Ben Jaggard. Ben Jaggard works in S&I, and he's a blast engineer. And he sort of gave us a lot of user stories about being on the site and being able to give people alerts, and not just a map, but alerts of when there's a blast, or we've been sort of working with that story. So, seeing some of our tech.
All right, so I'll go into the how it actually works now. So basically, we have the user phone, which we don't have over there, apparently. This thing. So this is essentially what it will look like. We're going to get time to build a case, but this little kit here goes onto the back of the phone, and it actually connects to our LoRa network. So we have 2 networks. We use Wi-Fi 2.4, and we also use LoRa. What is LoRa? LoRa is a low-power, long-range wireless technology. We can get upwards of about 40 kilometers with LoRa, and obviously Wi-Fi about 50 meters. So we can create a mesh network with LoRa by rebroadcasting whatever data it receives, and so the device can we have this device here, show it. It's actually a lot bigger because we didn't have time to order the right part, so we had to sort of mesh what we had. The end device is actually a lot smaller, less than half the size of this. This actually will go on a hazard, so at a working heights area, on a cone, in a car, on a truck, whatever hazard you want to identify. This is just any person on site can carry this around with them and receive data from our network. I'll just quickly go and show you. I'll just show you quickly. So it's not showing. Why is it not showing?
makes clear here that the two types, there's the with and the without. So you can actually have just the phone. You don't actually have to carry any.
So this bit of kit here is actually just for LoRa. So this is the long range, low power device. So this can go 40 kilometers. Personally, I tested this and I had about 8 kilometers range. So you can essentially mesh a whole site with that without having hundreds of nodes. You can have two and basically mesh your whole site with the data you want to receive. So I'll just go through this. This is the wireless mesh. So this is the data that's being sent and received on the wireless. And this is the LoRa mesh. So this is the data that's sent and being received on the LoRa. At the moment I have it at a 1 second, sub-second update, but it can go to 0.2 seconds. It's only in a second because just so we can read it really, otherwise it's just too fast. You can probably see that we have longitude, latitude, speed, altitude for whatever device. This is the blast zone, working height. So there's 2 different nodes that are running at the moment. It's essentially the same information over here. It's just reduced so that we can send it quickly and not have to spam it with stuff we don't want to read. So communication between the phone and the LoRa, we use UDP. I won't go into that too much, but this is the prototype progression. So this is what we initially start with. This is a Raspberry Pi 3 and a Dragino. The Dragino has GPS and LoRa. We then realised we can actually use a Pi 0, it is the same thing, and then we also realised we can actually do it with just the low Pi itself. So this. Thanks.
Questions?
I always struggle with Wi-Fi networks. and today is a great example. But how stable are these devices? And the question is basically to everyone. But when you have a safety device, people become very reliant on it. And if it fails, there's not an option for failure. The last presentation we heard about fail safe. So you know, ticking box, well done, because that's where we want to be, right? Ultimately, safety for our people, care for our people. How stable is this platform? That's question 1. Question number 2, the LoRa network, line of sight, obstacles, mine sites. So typically, you dig a hole. That in itself creates quite substantial obstacles. How does this technology deal with that?
Okay, so question 1. The reliability we have, that's why we have 2 networks. So we have redundancy through LoRa and Wi-Fi. So that's our sort of redundancy system for that. In case one network fails, we always have the LoRa network or the Wi-Fi network to back it up. So Wi-Fi obviously smaller range, but more data. LoRa network, more range, but less data. I'm sure we can get more data in there, but it's just a matter of time really. Question 2. So it's essentially the same as your phone. So your phone uses Telstra Optus network is, it's around that range. I actually don't know what it is, but 900 megahertz network, which is what we're using for LoRa. So it's pretty similar. Underground, you're probably not going to get too much, but if you have the right, you can mesh it. So if you have line of sight underground, you can always use that to get further underground if that's what you want to achieve. So it's always there through the mesh network.
Yeah. So we use trilateration. So if you have more than 3 beacons, okay, you can, and they are connected to each other, you can get the location of the person moving into the mesh.
I think some of the beauty of the system is that you don't need to have all the beacons on. So we're sort of recommending 3, so you can actually, we recommend 5 for that redundancy, but 3 will give you that trilateration, which I think one of the other teams have already talked about. So when a phone goes off, then you can actually get alerted that someone's gone off. We can also alert, because all of them are broadcasting to each other. If one fails, then the other ones will actually rebroadcast what that last one used to be broadcasting. So they're all fully sort of redundant. You don't have to be standing next to a particular one. And I could also say, well, we want to protect somewhere in Newman from here. So we can sort of go, all right, if you want to sort of go, well, someone's walking into that sort of area, well, he'll pick up their GPS and send it to you.
It's not just GPS data, it's whatever you want, sensor information or anything really, we can send over LoRa and it'll mesh to wherever you want to go. So we do use it's an open source trial iteration algorithm, which I had a demo, but I didn't get time to, unfortunately. But basically how it works is you can have a device that does not have GPS, but we can use trial iteration to determine its location through signal strength. So that's something that I personally think is pretty cool. I'm going to do that.
Cool. Yeah, one more question.
So a question maybe for you to answer, I'd actually have this for a few people, is when you use the GPS with the triaxial acceleration, are you able to determine elevations as well, reliably?
Yes, if you have the location reliably with the GPS units, you can, and you have more than one unit, more than 3 units. The more units you have, the more accurate you will get.
Just really quickly, I don't have a question, but just a compliment. I love the way it started with a user story. I think that was really impactful, and then kind of worked backwards from there, and also utilising hardware that's already in people's pockets is obviously a pretty great idea from an operational deployment point of view. So well done.
All right, good stuff. So we're going to take a quick break, 5-10 minutes, and then we're going to come back and we're going to keep going. So take a break if you need, and we're going to keep going.
I have so many questions. How hard? Okay, so I appreciate the offer, but I also, and I don't have an operational background. Which is by definition distracting. How big a week is it to translate all this into? Well, I guess 2 questions. How big of a problem is it to have all this that you are picking up while you were doing everything, and they may not always be able to, I mean, they stop, you say, but that strikes me as a challenge. So is that a challenge? If it is, how big will it be to do at least some level of
So that would be feedback that is actually sort of decision I get the work so if you're out there that's
they're limited to what we have.
Some of us like since we didn't actually
for it and somebody to go with the individual here
such a short time. So I say it's just like if I had information about this, you want to take at least like myself like I've done
for
really
really serious
and I said it at the end of the like
People come over and
steering.
But how come a whole just be ready?
Never had that. I was working with me and someone came.
The question I've got is probably unfair to answer. If we take like working from side of Magic, regardless of how good.
All right, so if you want some food, there's
something
there is some
extra
food here.
for workers to do. So to go 5, 6, 7, maybe more for the permits need to be completed before they take the task. Unless the new technology thing is reducing or simplifying some of that, how will it ever be a benefit to them? That's kind of some of what I'm seeing, at least objectively as well. Yeah, great, but how's that going to help with the system? Do you have a view, like from a whaleback perspective? Is there an opportunity for like, how easy is that conversation to have? I think the technology is right. I think it's going to benefit. And now there's using to drive the simplification of our previous tools and processes, or is that just a sacred cow?
Look, it needs to be challenged. You never end up in hot water when you end up in a disastrous situation. Someone didn't do something, and someone didn't conform to a procedure, and no one ends up in a place where I'm going to get up out of bed today. I'm going to really screw this up. I'm going to put my life on the line. No one wakes up with that objective. So inadvertently, the challenge says or didn't know, or didn't really know the consequences. And however we can streamline that and make it simple for people to understand the real risk associated with it. It's quite
it's almost that's the that's the beauty of a tool that comes in. It doesn't have to be technology, but if it's something that removes an existing process or simplifies an existing process, then regardless of how flashy it is, it's going to have the most positive impact.
I worry that so much technology and safety. So if something technology breaks, 5-10 years down the line, we've got a new generation of people come in.
That was Pat's point, the reliance on the safety tool or the technology, and then you turn that part of the brain off.
I'll give you 2 examples of that. I remember listening to a radio program 7 years ago, and it's quite substantial, I remember, but because we're dealing with the same issue at an individual on talkback radio goes, I've just bought a car with proximity sensors with the alarm and all that stuff. He said he'd been driving for 30-something years, never reversed into it. He's got this technology, and for the first time, brand new car, reversed into it. And he started to took around our DSS system for the team. And people now are saying that it's all right on time because my seat's going to buzz and wake me up. So I'll stay up tonight.
I'll just redline it.
I'll have that extra view, but I know my seat keep me safe. I know that seat's got an availability of 94%. So 6% of the time it doesn't operate. So if you put the bullet in the gun, you pay attention to it's going to catch you. Hey, mate.
How are you finding it?
I love it.
I look like it. You asked me a really good question.
What do you expect?
I was going, do you stop that? Give me someone to.
It's really good. It's going to be hard to score. Some of the technology freely available, it's created for it's free. Like that last one, that Laura stuff.
Yeah, Laura's the newest in the but I won't stand. But actually, the hard like, they're the ones that have to come.
Yeah, very similar to the system.
You can put. Imagine, like we're saying, like, when we do the $3 million, I can't remember if I had $3,000 worth of fine. Imagine what you do.
Yeah, I can hear the debate now.
Hello?
Yeah, that's it.
Yes.
Thanks.
We'll just wait here. Wait here on the call. And then, I'll take a log in on Skype if anybody wants about 10 people.
Okay. I just keep it cool. It'll be on and yeah, when you come back, we'll put the screen on.
All right, everybody, come grab your seats for the second round.
Come on down, we're gonna get the second round started. There's 5 more sheets to go.
Keep talking.
And please come and take a seat.
Hello?
Yeah, that's good.
And at the end, we got prizes and awards to give out.
Yeah.
Yeah.
Come on down, grab a seat. So the next one's remote.
So, Duke, I'll leave it to yourself leave it to you to introduce yourself. But and just before you jump into your presentation, I've told you also that, including with the other teams, there's a 7-minute timing. So if you have a timer on your side, it'll be better off because you will not be able to see the small little timer sitting on the desk over here. All right?
Yes. All right.
Awesome. Take it away.
All right. Can you bring up next slide on the screen?
Yeah.
Oh.
I can see. You got it.
Right.
We've got the share screen up.
Okay. So my name is Dick Fan from Team 9. From Adelaide. Our group has, our team has 4 members, another one from Adelaide, South, and Whitehouse from San Francisco, and South from Toronto. So that's why our team name is San Francisco, Toronto, and Adelaide. So we talk with talent here to develop a prototype, that work in a mesh network for set device. Right. So we sort of look into like a few small challenges that we would like to tackle. We need to identify the suitable networking solution, like a solution that has range, power consumption, and bandwidth that's suitable for the application. And then the second thing that we want to challenge is like integrate a GPS model and evaluate its performance to see if it's suitable for the application we want to build. We look into power consumption to see if our prototype can last within like 2 to 3 days with a battery pack, and then we prototype our node. So look at the communication. So what is suitable? There's a lot of communication, like selection now there, Bluetooth, Wi-Fi, and Zigbee. So the Raspberry Pi Zero that given to us has like Bluetooth and Wi-Fi earphones, and we do a quick analysis to see if it's suitable. And it seems that Bluetooth is really short range, so 10 meters, so it's not really suitable. Wi-Fi although can be like longer range, but it has a few limitations. For example, it has like higher power consumption. So if we use Wi-Fi, that cannot really last really very long. And also like it has limitation of how many nodes that you can use in the network. So we decided that we use Zigbee, which has a number of nodes in the network can be like up to 65K, 1,000 nodes, which is excellent. Also the range is also excellent. So here's our prototype. There's a delay. That's right. So here's our prototype. So the prototype, our prototype has a DGXP Pro on top, so on the right hand side. It has an excellent outdoor range of like 3 kilometers, indoor range around 90 meters. It's really low power in sleep mode. It only consumes like 1 microampere, so it has an excellent like power consumption. On the left hand side, we have the U-Blox Neo 6 GPS modules that can provide like location, heading, and speed. And we have the Raspberry Pi Zero underneath. Right, so here's our prototype. So we have built 3 prototypes, but like actually they're just the same hardware. So our goal is to build a simple, reliable, flexible, and scalable. It means that we have like just one hardware underneath, and on the prototype on the right hand side with a cabinet, you can see there's a few switch. So depending on which switch you select, then it can be different device. So this Zigbee network, it does not really require any infrastructure. So doesn't matter how many nodes, you can just like turn on the node, choose a type, and throw it to the field, and it can be just like one active node. So that's its idea. So depend on the how many type of like how many nodes you want to put. It's just like put it on a corner barriers or a trucks or whatever vehicles, and all the information, it's just like location, speed, heading, will be broadcast through the network. So all the nodes you hear will receive information like of the other node in the network, and it will be its own table of like the location of other node around it, whether it has a code next to it, or 3 code next to it, or barriers, or there's a truck coming. On the truck, there will be a same device that also receive all the information from the Zigbee network, built on table, and then it communicates with a display device through Bluetooth. And the display device will draw the zone, whether it's safe or not, or generate an alarm when needed. So what we have done, we have a transmitter device with like 5 meter accuracy. We can broadcast information, location, heading, velocity ID, type, tab, and we have a display device on, for now it's on PC, that can show the location of all the nodes in our network. And all our node is really small and it is low power. So here just like one simple demonstration of like in the network how the information is. So you can see here, so we have a few nodes in our network, and all the information is sent, so it just broadcast to all the other nodes in the network. And the receive node will be with a table of like I said, like its neighbor node. All right, so the power consumption, looking to like how much power it uses. So our prototype uses around 140 milliampere, 3.7 volt power supply during like normal mode, it's not just like operate without transmission, and it uses like 500 milliampere during active transmission. So now like we only transmit one every 5 seconds, so it's short period, like just few milliseconds. Transmission every 5 seconds. So we think that a 10,000 milliampere hour battery pack is enough to supply our node for 3 days. I'm not sure about the other node, but like if you use Wi-Fi, well, I don't think it can last that long. The next step is to refine our hardware design, because now there's a lot of redundant, so we can make it more efficient in power consumption, make it smaller. So now we have the display stuff on API on laptop. We can make it on Android. It's better. And we have to test model in a larger scale to see if we have 1,000 nodes, the real like
Questions from the judges?
Yeah, just a quick one from me. Interested to know what kind of data you captured and kind of conversations you had with the mentors to frame this. Like, how did you kind of validate what solution you were building here and what kind of data points?
I just to talk with the friend, and we come up with a solution that we think that we have a solution that require no infrastructure. You have a device that you can just power on. It should be simple, require no configuration. You just like power on, choose some type, connect to a one or the areas, it just work on itself.
Okay, thank you.
Thank you.
So just a quick kind of follow-on question for me. What did you kind of find during this challenge in terms of the scalability of Zigbee and kind of number of nodes, both from a spatial scalability and kind of data transfer across it?
Right, so the specification of the XP node, say 3 kilometers. I have tested indoor at like 50 meters. I have a network that I set up here with like 50 nodes. I don't think that I have any problem with that. And I think there's a large network in Europe. They have set up like a few thousand nodes without any problem. So I think like on scale size, I don't think that is really a problem. But the problem is like how much data you send. But like for this application, the data is not much. It's just like GPS, like location, long, just a few bytes, but a few seconds. So I don't think that's a real problem. The bandwidth of network.
Hi, it's Patty. Look, thanks very much for your contribution as well. Again, another fantastic result. The question I've got for you, you spent a bit of your presentation, you spoke to power consumption and draw.
Oh, okay. Actually, they should be all the same because the device on the equipment or on the field, the only difference is the device on the equipment will use more information. It needs to send to the display. So display is a different thing. It is not a take or draw power from the node. So the display will talk with the node on the Bluetooth. So for the node in the truck, it will use more power on Bluetooth, but like it is not much. So all the nodes just the same. The display device are different. It's just like a normal Android that can talk to a Bluetooth, receive data through a cardboard via Bluetooth, for example, and display information.
Okay, and the devices that are battery powered, those devices that are the beacons, the cones, these devices, have you looked at innovative solutions, whether it be solar or something of that description, so you don't have to change batteries out? Because that becomes quite problematic when you start to scale these devices.
Yeah, that can be, but like I think for this type of device, I think you have to keep it as simple as possible. So like solar is good, but like it makes the device more complicated and maybe easier to break down. So for example, on the code, for example, the XP can install, it can like stay as long as like 3 years. It only consumes like 1 microampere. So for a code, it only need to update its location like once every, like say 10 hours or 12 hours. So like on battery, it can stay for a year, I guess. So I don't think solar is needed.
Thanks.
Thank you.
Any other questions? Good.
Thank you.
Okay, next team up, Clarks, come on down. Here we go. You're good. Keep going, man.
All right, how's it going, guys? We are Team Klog, and we're working on Challenge 2, trying to provide a solution using distributed safety devices. So we've got a pretty diverse team. We've got myself, Adrian Rochak. I'm studying to become a network engineer. We've got Nathan, who's studying to be a software engineer. We've got Stephen, studying to be a mechanical engineer. And we've also got Nicholas, studying to be a mechatronics engineer. So the goal of our team is to provide a solution the BHP to increase safety for frontline personnel in the mining environment. And the way we're going to be doing that is by creating a solution that will be robust, safe for the user, reliable, and have good power consumption, and also batchable, and we'll explain why shortly.
Cool. And because we have such a diverse mix of people in our team, we thought we'd take the opportunity to sort of approach this problem a little bit differently. What we really wanted to do was not only deliver a hardware solution, but a software solution to go with it, to make it easier for the end user to use, even if you're not tech savvy. Basically, our different backgrounds were a huge advantage while we were working through these challenges.
Go back to your slides. I forgot something, guys. Sorry. So I wanted to go in and talk about a user case. So as you can see, I've got a really good example. We've got a car here. So a person was going to an exclusion zone, and they have left the car unattended, I hope. And so a big heavy vehicle has come along, working in his mining area, and he might not be able to see the vehicle, and he has gone across and crushed the vehicle and destroyed it. So our solution is trying to provide a warning system to show the driver and other users around where obstacles are, if there are nodes in the way, and notify them as well. And also provide tracking for BHP to find out issues, because something like this happening on the site can cause BHP to shut down our mine site, have investigations, which translate to profit loss for BHP. Again. Okay, so I guess the beginning of our solution, we decided to go with a mesh network, and we chose the application of Batman mesh. So using a mesh network is pretty much a peer-to-peer network using the 2.4 gigahertz band of Wi-Fi. So what that means is we can distribute thousands of nodes across the mine site, and if one node goes down or multiple nodes go down, it will always find a route to get there. So the algorithm that Batman uses is kind of like OSPF, where we find the shortest best path, but their algorithm and calculations